Hey guys, I want to talk to you about simplifying radicals. Usually simplifying cubes is something that people struggle with, or simplifying variables. So I want to get a little pre-practice in, so that way before class you can ask whatever questions you want, or you can start coming up with the questions that you want to ask. So I think that a good idea for this is to have your list of squares, list of cubes in front of you. I went ahead and wrote out a whole list. So like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, all the way down to 19 squared is 361, and 20 squared is 400. So these are all the squares. The benefit of having them is that you'll know what the perfect squares are and what their square roots are, meaning the square root of 144 is just 12, the square root of 196 is 14, the square root of 324 is 18. So it'll be helpful to have your list of squares and also your list of cubes, especially cubes. People struggle a little bit more with cubes. If I ask you what's the cube root of 343, now you can say right away that the cube root of 343 is 7, just because it's on my list. Right, so the benefit of this is that you'll be able to do a lot of the cubes very quickly. You can come back and refer to it as much as you need to. But really this chapter relies on one fact, and that's that the radicals always separate over multiplication. It's called the product rule. It says that if I'm taking the nth root, it doesn't have to be a square root, it could be a cube root, a fourth root, a fifth root, doesn't matter, of something like a times b, then it turns out that I can just take the nth root of a times the nth root of b. And so generally this is pretty nice for numbers. Why? Because if I take, say, the square root of 8, what you see is I don't know what the square root of 8 is. It's almost 3, but I could simplify it, meaning 8 is 4 times 2, where 4 is a perfect square and 2 is not. The benefit of doing that is that I can separate the radicals to be the square root of 4 times the square root of 2, so that when I take the square root of 4, the radical goes away. The first radical goes away to leave me with 2 square root of 2, because I don't know what the actual square root of 2 is. So I've simplified the square root of 8. It is just 2 root 2. It's reduced. It's simplified as much as possible. Let me show you something like the square root of 32. That's a good example. We'll probably do it again later. Your logic for these problems should be, what's the largest perfect square or cube, depending on what I'm working on, since I'm dealing with a square root here. I want to know what's the largest perfect square that goes into 32. So this is why it might be nice to have your list of squares. I'm saying, okay, what's the largest perfect square that goes into 32? Well, 4 goes into 32, it's 4 times 8. Okay, 9 doesn't go into 32, but 16 does. 32 is 16 times 2. 25, 36, none of those are going to go in. So 16 is the largest perfect square that goes into 32. So then I can say, okay, well, the square root of 32 is the square root of 16 times the square root of 2, so that I get 4 square root 2 when I simplify. Notice, though, that if I had taken the square root of 32 and rewritten it as 4 times 8, I've technically simplified a little bit, but I have not simplified completely. Meaning, square root of 4, square root of 8 is 2 square root of 8, but the square root of 8 can actually be broken down further. So I'd have to start over and say, okay, well, 8 is 4 times 2, so that this becomes 2 times 2 square root 2, and eventually I get the same thing. I still get 4 square root 2. So I had to break 8 down. The largest perfect square that goes into 8 is 4. The square root of 4 is 2, so I multiply it with the other 2 that's outside to give me the 4 that I got originally. So it's much easier to just take the largest perfect square that goes into your radical. Once you know that, then you can separate it and take the square root of the first term, not the second one. What you should see, one last option, is that if I had the square root of 32, it would be kind of silly for me to break it up any other way. Well, maybe 32 is a bad example. So let me use like the square root of, say, 24. Let me just create a new page for this. Let's do the square root of 24 on the next page. Say I had the square root of 24, and I wanted to simplify it. The largest perfect square that goes into 24 is 4. This is the square root of 4 times the square root of 6. I always put the perfect square first because then I'm going to take its radical. The square root of 4 is 2 square root 6. So I've simplified the square root of 24. But notice that it would be silly for me to try to break it up any other way. Like a lot of people ask, well, that's true, it is 4 times 6, but it's also 2 times 12. And I say, yeah, but look, 2 is not a perfect square, I can't take its radical. 12 is not a perfect square, I can't take its square root. So I'm stuck. That doesn't help me break down any further. Same thing, it would be silly to break it down to be the square root of 3 times the square root of 8. These are no good choices. I always want to make the first one a perfect square so that I could take its radical and actually simplify it. So these are not the best choices. Alright, so then the same thing is true for cube roots. Like if I had, let's create a new page. Let's say I had something like the cube root of 54. Cubes usually mess people up because they're so used to working with squares. But if I'm dealing with a cube root, if the index on my radical is 3, then that changes the problem completely. I'm not looking for the biggest perfect square that goes into 54. I'm looking for the largest cube. So if I go back, I say, okay, does 1 go into 54? Of course, but that's not going to help me. 8 doesn't seem like it goes into 54. No, 8 doesn't go into 54. 27 does go into 54. It's 27 times 2. And that's the last perfect cube that's smaller than 54, so 27 is my choice. What that means is that I can break the cube root of 54 up to be the cube root of 27 times the cube root of 2. Again, it's a big deal that I bring the index along because I'm taking the cube root of 27. The cube root of 27 is just 3. And then the cube root of 2, that just comes along for the ride. So the cube root of 54 can be simplified to be the 3 cube root of 2. And so, like I said, the bigger your list, the better that the easier these problems will be, essentially. So I could do something like the cube root of 16. Notice that 16 is a perfect square, but I'm dealing with a cube root, so I'm kind of stuck now. The only cubes that are smaller than 16 are 1. 1 cubed gives me 1, or 2 cubed gives me 8. So 8 does go into 16. I could separate this to be the cube root of 8 times the cube root of 2. Again, all I'm thinking of here is what's the biggest perfect cube now, because I have index 3 that goes into 16. Well, the cube root of 8 is 2, and then the cube root of 2 I can't do anything with, so I just leave it simplified. Some of the values might get big because you do have perfect cubes. Like maybe I have something like the cube root of 875. Now it looks a little tough because I have cubes. The cubes blow up quickly. I know that it has to be at most one of these numbers less than 9, right? So I'm just looking for the biggest number that goes into 875. Since it's 875, since the last 2 digits are 75, I'm thinking that maybe 25 works. 25 is not a cube though. I do have a cube with 125. Let's see if that one works. Can I rewrite the cube root of 185 as 125 times something else? It seems like It's 7. 7 times 125 gives me 875. But the good news is that I know what the cube root of 125 is. 125 is 5 cubed, so the cube root of 125 is just 5. Okay, so then that's how you simplify radicals with numbers. You can try them. Some of the numbers will get big. Some of the numbers will be smaller depending on what problem you get. But I also want to talk about how to simplify using variables. So if I'm dealing with like the square root of x to the 7th, I want to know how to simplify that. The truth is, you could write it out as the square root of x squared, the square root of x squared, the square root of x squared, and the square root of x. Because x to the 7th is 2 plus 2 plus 2 plus 1, right? If I'm multiplying things with the same base, I can add their exponents. 2 plus 2 plus 2 plus 1 gives me x to the 7th. So when I take the square root of each of these x squareds, I just get an x out, assuming that x is positive. So I get 1x, I get another x, I get another x. This gives me x cubed, x times x times x. But then this last square root of x, it doesn't come out of the radical, it just stays the square root of x. The question is then, is there a shortcut? And the answer is yes. Whatever the index is, you just ask yourself, how many times does 2 go into the power? How many times does the root go into the power? Well, 2 goes into 7 3 times with a remainder of 1, right? So I can just say 2 goes into 7 3 times so that I get the power on the outside. And then when I actually do the division, I get a remainder of 1. That gives me the power on the inside. And so that would be really helpful, like if I had the square root of x to the 95th power. I don't want to have to write out the square root of x squared times the square root of x squared a bunch of times. I don't want to have to do 95 x's. So rather, I just can ask myself that same question. How many times does the index, how many times does 2 go into 95? Just do the division. 2 goes into 9 4 times, leaving me with 8, so that when I subtract, I get 1. I bring the 5 down. 2 goes into 15 7 times, so that I get a remainder of 1 again. What does that mean? That means that the power on the outside is 47. There are 47x squareds in x to the 95, but when I take the square root, I just get x to the 47th. And then the remainder is 1, so that means that there's one single x left on the inside, no power left over. You can do the same thing with square roots or cube roots or fourth roots or fifth roots, doesn't matter. Like if I ask you, what is the cube root of x to the, say, 17th? Maybe you can see this one. You know that 3 goes into 17 5 times with a remainder of 2. Right, so there's a lot going on here. I'm saying that 3 goes into 15 5 times with a remainder of 2. If you have to do the division, fine, do it. 3 times 5 gives me 15, so that when I subtract, I get the remainder of 2, just like I said. But also make sure you bring the index along. I'm not going to circle it, maybe I'll underline it, that the index has to come along. Because if I wrote it as x to the 5th, and then I put the radical without its index of x squared, this looks like x to the 5th square root of x squared, and those would cancel out. So you got to make sure you put your index, otherwise the problem's incorrect. So the idea is, how many times does 3 go into 17? It goes in 5 times. What's the remainder? The remainder is 2. And so really you should practice this a bunch. We'll talk about it. I'll give you actually another way to try them, but I think it would be best if you just practice this method most. Like say I had the cube root of x to the 51st power. Well, in this case, 3 goes into 51 17 times, it goes in perfectly. So if there's no remainder, that means that everything came out. The cube root of x to the 51 is just x to the 17th. There's no remainder, no cube root left on the inside. But then just changing the values up a little bit, you can get extra practice. Simplify something like the cube root of x to the 20th. 3 goes into 26 times, so that means x to the 6th comes out. I still have a cube root, but whatever left, however many x's are left, is my remainder on the inside. 3 goes into 26 times, leaving me with 18, so that when I subtract, I get 2. The remainder is 2, so that's the value that goes on the inside. And so what you'll see is you're going to be asked to simplify kind of a mixture of these things. You should practice the variables, practice the numbers separately, because you're going to be asked to do something like simplify the square root of 9x to the 5th. Remember what the product rule says. It says you can just deal with each piece individually. The square root of 9, I know what that is. It's just 3. And the square root of x to the 5th, I could do that off to the side. Remember the index here is 2. 2 goes into 5 2 times, so that I get an x squared on the outside. 2 goes into 5 2 times, so that I get x squared on the outside. On the inside is the remainder, so when I do the subtraction, I get x to the 1st. Or I don't have to write the power, I can just write it as x. So let me try another square root, and then I'll do a cube root one. Say I have the square root of 25 x to the 9th. Then again, just take the square root of the number portion, simplify that if it's not a perfect root. Take the square root of x to the 9 and simplify that portion. Well, in this case, the square root of 25 is 5, no problem. But I know that some x's are going to come out. How many come out? However many times 2 goes into 9. 2 goes into 9 4 times with a remainder of 1. Right? 2 goes into 9 2 times and gives me a remainder of 1. Let me try a cube root one, and actually I think let's pick one that doesn't simplify, the number doesn't simplify completely. Like maybe let's deal with the cube root of, let's say, 54x to the 7th. This is a good problem because I've already done the cube root of 54 and the cube root of x to the 7th. If you want, you could rewind to when we did this example. We simplified the cube root of 64. We said that 27 is the largest cube that goes into 54. It's 27 times 2, so that I get 3 cube root of 2. Right? We already knew that technically. But now I want to know how many times does 2 go into, I'm sorry, it's a cube root. So make sure you bring your index along. How many times does 3 go into 7? Well, 3 goes into 7 2 times with a remainder of 1. So that means 1x is left on the inside. Right? 3 goes into 7 2 times with a remainder of 1. So x squared pops out. The cube root of x stays in. The point is, I got 2 separate answers for each piece. So now it's time to put them back together. I have to put them back together with everything that came out on the outside, everything that stayed in on the inside. Meaning there's a 3x squared that comes out. There's a 2 and an x inside the cube root. So this is my final answer, 3x squared cube root of 2x. It looks kind of like a lot, but all I'm doing is each piece individually. I'm taking the cube root of 54, I'm taking the cube root of x to the 7th. So go back and practice each of those pieces, and then fast forward back to this part of the video and see that I'm really just putting them together. The 3 and the x squared are on the outside, so I put them together on the outside. The 2 and the x are inside of a cube root, so I put them on the inside of the cube root. Let me do one more for you, and then I'll send you off to try the pre-problems of the day. Let's say I have 128 x to the 10th. inside of a cube root. Sorry, let me rewrite this so that it's neat. The cube root of 128 x to the 10th. Well, if you take it in pieces, you have to do the cube root of 128, and you have to do the cube root of x to the 10th. At this point, I think most people are probably comfortable most with the variables. At least that should be the easiest, the quickest of the two. If you haven't gotten comfortable with them, try it. You really just want to know how many times 3 goes into 10. You could rewrite it as x cubed, the cube root of x cubed, the cube root of x cubed, the cube root of x cubed, and then that's 3, 6, 9. There's one more x left over. But really what this is doing, what this whole process is me just asking how many times does 3 go into 10. So it's not worth writing all that, I don't think. I think it's better to just do the division. Say, okay, how many times does 3 go into 10? 3 goes into 10 3 times. So that on the outside I have x cubed pop out. And in the inside of the cube root I have the remainder. Well, 3 times 3 gives me 9. When I subtract, I get 1. So I just get a single x left on the inside. The variable should be the quickest. The cube root, that should be the hardest part. You have to find what's the largest perfect cube that goes into 128. Look back at your list of cubes. You might want to pause it for a second. Look back at the list of cubes and try to figure out what the largest perfect cube is that goes in here. I think it's supposed to be 64. It's the cube root of 64 times the cube root of 2. But the cube root of 64, that's just 4 times 4 times 4. So it's 4 cube root of 2. Like I said, the numbers, they take a bit of practice, especially with cubes. You just got to ask yourself, what's the largest perfect cube that goes into 128? Now it's time to put it all together. What does this actually simplify to be? I did the number individually, I did the variable individually, but now I can say this is just 4x cubed along with the cube root of 2 and x. 4 came out, x cubed came out, 2 and x are left on the inside, but I want to emphasize the biggest point, that you bring the index along. Don't forget that this is a cube root of 2x, not a square root of 2x. All right, so try them out on MathXL. There's probably 4 problems, but I really want you to do one without variables and then one with variables. Practice each of them, and then that way you can have the specific questions. Maybe I'll even give you another method in class. All right, so I think it's a really good idea to practice these. These are the best methods, the fastest, but I'll show you another way as well. Let me know if you have any questions.